Every game, robot, and spacecraft simulator needs a rule for what happens after two bodies collide. They might rebound, latch together, or deform, but an isolated collision must not create momentum that no external interaction supplied. We will strip that design problem down to two equal carts on a low-friction track. One cart approaches, the other begins at rest, and the boundary marks the complete system that we will audit. Inside this boundary, a 1 kilogram cart moves right at 2 meters per second. It strikes an identical cart that begins at rest. 3 complete outcomes are waiting below. The moving cart might stop while the second cart takes its speed. The carts might stick and move together, or both carts might leave at the original speed. Which outcomes could an isolated collision produce? Choose every outcome that remains physically possible.
The velocity exchange looks possible, and sticking also looks possible. If both carts leave at the original speed, the outgoing motion seems larger than the incoming motion.
Give every cart its momentum, which is its mass multiplied by its velocity. The incoming total is 2 kilogram meters per second. The exchange outcome also totals 2. The stuck pair moves at 1 meter per second, so its 2 momenta also total 2. The last outcome totals 4. Without a positive external impulse, that extra momentum has no source, so the last outcome fails the first ledger.
Then momentum did not tell us whether the carts bounce or stick. It only rejected an outcome whose total momentum changed.
That distinction is the reason a collision needs more than one ledger. First, we need to see why the momentum total is protected by the boundary around both carts. The momentum totals rejected one impossible outcome, but we still need to explain why the total is protected inside this two-cart boundary. A collision does not need a mysterious new update rule. It needs a force acting over a short interval. During contact, that force rises and falls. The area under the force versus time curve is the impulse. The impulse is exactly the momentum change produced during that interval. The screen keeps the compact equation, while the physical action is simpler. Accumulate the force through time, and add the result to the cart's momentum.
If cart A pushes cart B, should the boundary receive the impulse on cart B as a new total momentum?
Cart B receives a rightward impulse, but cart A receives the paired leftward impulse from the same contact. The two arrows have equal magnitudes and opposite directions. Now add the momentum changes for both selected carts. The internal impulses cancel in the system sum. They transfer momentum from one cart to the other, but they do not create total momentum for the isolated pair. Only an impulse that crosses the selected boundary can change the total momentum inside it. If the track pushes significantly during the collision, or if we select only one cart, the external term is not zero. Momentum conservation is therefore a conditional statement about a declared system, not a magical property of every object considered alone. These lanes repeat the same incoming masses and velocities, only the contact model changes. The left bumper stores deformation briefly and returns it. The right coupler remains deformed and keeps the carts together. Total momentum must remain the same in both lanes. Does that force the carts to finish with the same motion, or can the two lanes end differently? Choose before the carts move.
I expect the same total momentum to force the same final motion. Otherwise, I do not yet see what momentum is predicting.
Release both incoming carts together. Each contact first compresses. The elastic bumper springs back, so the first cart stops and the second cart leaves at 2 meters per second. The sticky coupler does not restore the original shape, so both carts leave together at 1 meter per second. Both lanes still end with 2 kilogram meters per second of total momentum. The same incoming state has produced two visibly different outcomes, and the momentum ledger accepts both of them.
If momentum accepts both outcomes, what measurable difference tells us what the bumper did?
We need to ask how difficult each final motion would be to stop. An identical braking experiment will make that difference visible. Momentum could not choose between the bounce and the stick, so keep the same 1 kilogram cart and ask a different physical question. How difficult is its motion to stop? Both lanes use the same cart and the same constant braking force. The upper cart begins at 1 meter per second. the lower cart begins at 2 meters per second. Will the faster cart require twice the stopping distance or 4 times the stopping distance? Choose before the brakes act.
I expect twice the stopping distance because the lower cart begins with twice the speed.
Release both carts into identical braking strips. The upper cart stops after 1 distance unit. The faster cart is still moving at that point. It finally stops after 4 distance units. Doubling the initial speed has quadrupled the stopping distance under the same opposing force. The reason has 2 parts. With the same braking acceleration, twice the initial speed takes twice as much time to remove. During that longer stop, the cart also has twice the average speed. Twice the stopping time multiplied by twice the average speed produces 4 times the distance. When a force acts through a distance, it transfers energy. Physicists call this transfer work. The distance experiment therefore measures a motion budget, how much work the cart can perform as it is stopped. At the same speed, twice the mass takes twice as long to stop under the same force and travels twice as far. The work budget is therefore proportional to mass. We call that budget kinetic energy. For a mass moving at speed v, the kinetic energy is 1/2 of the mass multiplied by the speed squared. The square records the 2 speed factors we just saw, stopping time and average speed. Now return to the 2 1-kilogram carts. Before either collision, only the first cart moves at 2 meters per second. 1/2 times 1 kilogram times 2 meters per second squared gives 2 joules. After the elastic collision, the second cart carries the same speed, so the resolved kinetic energy remains 2 joules. After the sticky collision, 2 1-kilogram carts each move at 1 meter per second. Their combined resolved kinetic energy is 1 joule.
Did the other joule disappear when the carts stuck together?
No energy disappeared. The simple cart state no longer resolves that joule as translational motion. Depending on the coupler, it can enter lasting deformation, vibration, thermal motion, or sound. Momentum constrains every isolated outcome. The material response determines where the energy moves and which compatible outcome actually occurs. The 2 physical collision models close the momentum ledger for an isolated pair. We can now use that same ledger to audit an implementation. A simulation can satisfy an equation locally and still assemble the system incorrectly. The left update applies equal and opposite contact impulses. Their total is 0. The right update contains a small but common implementation error. It copies the same impulse direction onto both carts. Each individual line still resembles an impulse update, but the pair now receives a net impulse from nowhere. In the correct isolated run, the total momentum residual stays at 0 up to numerical tolerance. In the bugged run, the residual grows immediately. The ledger has localized a failure in the assembled update without requiring us to judge the motion by appearance alone. A useful audit asks 4 separate questions. Which bodies are inside the selected system? Which impulses cross its boundary? Which collision response has the model chosen? Did the numerical update apply every impulse with the correct sign and to the correct body? These questions keep the force model, the boundary, the material response, and the implementation from collapsing into one vague idea.
If the momentum ledger closes, have we proved that the collision model is physically correct?
No, the ledger does not prove that. Closing the ledger is necessary for this isolated test, but many incorrect models can conserve the same total. To explain a recoverable bounce, we need somewhere for energy to live during compression. A spring gives us the simplest visible version of that storage. This composite begins at rest inside an isolated boundary. Its left fragment has a mass of 1 kilogram. Its right fragment has a mass of 2 kilograms. A stored internal energy release will push them apart. Must their speeds have equal magnitudes? Must their momenta have equal magnitudes? Or must both fragments remain at rest? Choose the statement that the momentum ledger requires.
The total momentum begins at 0, so the 2 final momenta must cancel. Their magnitudes should be equal even, though their speeds need not be equal.
Release the coupler. During the same interval, the internal forces give the fragments equal and opposite impulses. The light fragment travels left twice as fast as the heavy fragment travels right. Their momentum arrows have equal lengths because -2 + 2 is 0. Their velocity arrows have different lengths because velocity is momentum divided by mass. The 1 kilogram fragment has a speed magnitude of 2 meters per second. The 2 kilogram fragment has a speed magnitude of 1 meter per second. Momentum and kinetic energy are not two names for one quantity. Momentum constrains the vector total for the selected system. The interaction model determines how energy moves among the degrees of freedom that we resolve.
Can we follow the energy after it leaves visible motion?
Yes, but first we must distinguish recoverable storage from transfer into unresolved internal motion. The next experiment follows the same work budget through a braking strip, a spring, gravity, and a damper.